All right, so this is going to be the last video for the week. This last video is going to focus on naming organic molecules, and so we're going to get into not a lot of, but we're going to get into what are the basics of naming organic compounds. And again, naming is one of those things that students really have found pretty straightforward to pick up in the past because I give you the rules, you follow the rules, and you come up with a good name for an organic compound. So we'll go through this pretty quick. If you have questions and such, of course, please come to office hours, come to bring those questions to class, all that good stuff. There is an exercise available on D2L that deals with naming organic compounds as well, so you can look at that and practice that and get that skill honed as well. All right, let's switch this over. Naming organic molecules. All right, how do we name an organic molecule? Step one, find the longest continuous chain of carbons. All right, so I'm going to draw a couple of the constitutional isomers that we had on the last slide. So this is just 6 carbons in a straight line. We had this one, and we had this one. All right, so there were two, we'll draw the two others too since we're here. So we're going to find the longest continuous chain of carbons. So in this first example, the longest continuous chain is pretty easy. It's all the carbons just laid out in a row. So in this case, it's these 6 carbons is the longest chains. In this case, in the next case, we only have 5 carbons in a row, right? Because if we go 4 here, if we make this one carbon 5, then we can't go back and touch this one because that one's not connected to carbon 5. Same thing here. 1, 2, 3, 4, 5. And these two examples both have a longest continuous chain of 4 carbons, right? So there's no way to number these uh, that gives us more than 4 carbons in a row. So we have different chain lengths, even though all of these have the same molecular formula. All right, the second thing we're going to do is number the chain so that any side groups, right, any carbons that aren't already accounted for are on the lowest numbered carbons. Okay, so what does that mean? So for as an example here, I'm going to use this one right here. Right, so this compound, we currently have this carbon that's unaccounted for. We have a CH3 group up here, right, that we haven't numbered yet. And right now that's on carbon 4. But if we erase these and go the other way, right, and number it starting from carbon 1 on this side, we end up with the CH3 group attached to carbon 2. So obviously 2 is lower than 4. So this is the numbering system that we're going to use. We're going to use a numbering system that goes from right to left as opposed to left to right. Now, you can go either direction. It does not really matter. We just want to make sure that this number that has the group attached to it is the lowest. So for example, over here, this one is already fine because in this case, we started with this carbon as carbon 1. That puts the two groups that are the two side groups on carbon 2, right? If we numbered from the other direction, it would be 1, 2, 3, 4, and the side groups would be on carbon 3. This one, it doesn't matter because we have one group on carbon 2, one group on carbon 3. No matter which direction you number it, those numbers will stay the same. All right, now we number the parent chain by our set of prefixes. Okay, so if our parent chain has 1 carbon, then we would call it methane. So methane is, of course, just CH4. Okay? And there's no constitutional isomers of methane because the carbon has to be in the middle. Ethane is 2 CH3 groups stuck together, right? So that would be carbon-carbon. 2 carbons makes ethane. 3 carbons is propane. 4 carbons is butane. So these two over here are going to be butanes because we have a parent chain of 4 carbons. Butane, butane. 5 carbons is pentane, 6 carbons is hexane. So we have 2 pentanes. And we have hexane up here. Now, hexane doesn't have any other groups associated with it, so this one is done. Right? This is hexane. That's the name of that compound. So if we just see the parent chain, if we just name the parent chain, then that assumes that there are no other groups, right? We can't do that with these two because these two would both be pentane, right? So we need to talk about the side group. We can keep going. 7 is heptane. 8 is octane. And we won't really usually go above 8, but we'll do nonane and decane just to get to a nice round number. Right? So using the prefix, the meth for 1, eth for 2, prop for 3, but, pent, hex, hept, 8, 9, and 10 are there. Right? In these cases, because we're dealing with alkanes, right, alkanes are, as you recall from a couple slides ago, alkanes are compounds that have nothing but sigma bonds in them. Alkanes always have the suffix ane. Right? So the suffixes are going to be over here. So alkanes will always have the suffix of ane, ane. If it contains a double bond, anything that has a double bond in it, it'll end in ene with ene. So then you'd have things like pentene, hexene, etc., etc. Triple bond is going to end in ine with a y. And then, of course, you can have hexine, etc., and all those things. If it's a side chain, then the suffix is YL. So instead of saying methane or anything like that, we're going to say, for example, this group here, this CH3 group, is a 1 carbon group that's attached to carbon 2. And so this is going to be 2-methylpentane, right? So the 2-methyl corresponds to this group right here. Right? A methyl group attached to carbon 2. And pentane tells us that then the parent chain is 5 carbons long. So the name for this one you should be able to figure out. Again, we have a 1 carbon chain coming off the side here. And that is 3-methylpentane. So 3-methyl refers to this methyl group right here. Okay. Anytime you see a CH3 group like this, if it's attached directly to the parent chain, this is a 1 carbon side chain. It'll always be a methyl group. Okay. Now these get a little bit more confusing because we have more than one side chain. In this case, we have a CH3 group here and a CH3 group here. Inevitably, people ask me, is there any difference between H3C and CH3? No, it's just kind of showing that the bond is to the carbon, right? So the bond goes to the carbon and the carbon has 3 hydrogens surrounding it. So in this case, we have 2 methyl groups. So this would be dimethylbutane, or butane, excuse me. And then each methyl group gets a number. So we have a methyl group on carbon 2. We have another methyl group on carbon 2. So this is 2,2-dimethylbutane. In this case, again, we have 2 methyl groups. We have 1 methyl group on carbon 2. We have 1 methyl group on carbon 3. So this is 2,3-dimethylbutane. So now we have a different name for all of these constitutional isomers. We have 5 different constitutional isomers of C6H14, but we can differentiate between all of them based on the arrangement of those carbons. And we do that by finding the parent chain. Find the longest continuous chain of carbons. This is the parent chain. right? We use these prefixes, methane, meth, eth, prop, but, pent, hex, hept, oh my gosh, oct, non, and dec for to indicate the number of carbons in the chain. So that goes for parent chains and side chains. So number one, find the longest chain. Number two, number the chains so that the side groups are on the lowest numbered carbons. And then the third thing to do is to list the side groups with the appropriate numbering. Right? So 2-methylpentane is different from 3-methylpentane because where the methyl group is attached, right? 2,2-dimethylbutane is different than 2,3-dimethylbutane. Right. And this is the nice thing about this nomenclature is this really works because we're focused on the parent chain and how long the parent chain is. The more side groups you put on, the shorter that parent chain gets, right? And so you can have one methyl group on a pentane chain and still have C6H14. You can have no methyl groups on it and it will always be hexane, or you can have two methyl groups on it and you'll have one of the two options of butane. Right? But there's no way that you can draw two different structures that come up with the same name because necessarily they will be different. So this naming system works really well for organic chemistry. It can even accommodate heteroatoms, which we will talk about when we get to a little bit more of functional group kind of stuff. And we'll use this naming system throughout. Again, go do the exercise that's on D2L that works with nomenclature. That will kind of prep you to do these kinds of things and practice your drawing and naming. And I will see you again next week.